Hi everyone, this video is going to be about the mole and molar mass. In chemistry, we're constantly dealing with atoms, and one of the problems we have is that atoms are really small, and we can't easily measure out one atom, two atoms, even 10 or 100 or 1,000. They're very small. We can't weigh them easily on our scale in such small quantities. So we're going to have to address that by the type of units that we use. We're going to count them a whole bunch at a time. Instead of counting 1 or 2 or 10, we're going to count them in huge batches, 6.02 times 10 to the 23rd atoms at a time. So this thing called the mole, this special number, you do need to memorize it. We use it all year long. It's what we call a counting unit. Counting units are units that we use to count things in batches. When you go to the donut store, you usually buy donuts by the dozen. You can buy 1 dozen or 2 dozen. You can buy 5 dozen. And so the mole is like that counting unit, but for chemistry. We're going to measure 1 mole of atoms or 2 moles of atoms, 5 moles of atoms, 6.4 moles of atoms. It's a way that we can use more reasonably sized numbers because we're counting them in big batches at one time. 6.02 times 10 to the 23rd is a huge number. It has that many zeros on it. We use scientific notation because you can see if you had to write out all those zeros every single time, it would take up a ton of space and you'd be very likely to miscount how many zeros you're writing. You might accidentally add one, might accidentally miss one. So that scientific notation makes things much easier, especially when we're using our calculator. You don't want to get a problem wrong because you missed 1 zero. Sometimes we call it Avogadro's number. Avogadro was the person who decided that this was the number to use. He picked this pretty random number because it helped us do some conversions in a simpler way. It makes it so we don't have to always do the dimensional analysis. That's why it's a pretty random number. A mole is such a large number that our brain has a very difficult time understanding it and processing it. Our brains really can't conceptualize very easily. So a mole of soda cans would cover the surface of the earth, and it would have to be 200 miles deep to get enough soda cans. That's how many soda cans that would be. A mole of popcorn kernels would spread across the entire United States, and it would be 9 miles deep. If you wanted to count to a mole, it would take so long. If you tried to count by 10 million per second, meaning you counted 10 million, 20 million, 30 million, 40 million, 50 million, 60 million, it would take you 2 billion years to get to 1 mole. That's how big that number is. So even if we're counting by 10 million at a time every single second, and we never ever take a break to eat or sleep or anything, it would still take 2 billion years to count that high. So hopefully that gives you an idea how big this quantity is. The crazy thing is that you can hold a mole of atoms in the palm of your hand. It doesn't take up very much space. That's how tiny each atom really is. Sometimes we're not counting atoms. We might be counting molecules or compounds or ions. It doesn't really matter. We can use the term particles, and that's going to describe whichever discrete object we're counting. If we're counting an atom, great. If we're counting an entire molecule at one time, we can still have a mole of those. When we have a formula like H2O, if we have 1 mole of molecules and we broke it apart, there would be 2 moles of hydrogens and 1 mole of oxygens. Here's a funny song. I'd like you to pause it, watch this video. It's a really strange one. It's a funny song. It gets stuck in your head. The graphics have to do with a video game. It's pretty weird, but it has some great analogies in it that help you really see how big a mole is. One thing that people sometimes have problems with is they mix and match the concept of counting objects versus weighing them. So if I have a dozen donuts or a mole of donuts and compare that to a dozen atoms versus a mole of atoms, well, 1 dozen donuts is 12 donuts. 1 dozen atoms is 12 atoms. But a dozen donuts is going to weigh more than a dozen atoms. So make sure that you're really trying to keep your brain straight in the difference between counting how many objects we have, but how much they weigh is going to be a completely different story. An atom is such a tiny unit, or a tiny particle, that we want to use a special unit. Measuring them in grams is pretty annoying because you would have to have a teeny tiny number. You'd have a very negative exponent on your scientific notation. It's not a very practical size to use. So they invented a new unit called atomic mass unit, and they just decided, hey, let's make 1 AMU the same as how much 1 atom of hydrogen weighs. So they figured out that hydrogen weighs 1.66 times 10 to the minus 24 grams. Carbon weighs 1.99 times 10 to the 23rd grams. Oxygen weighs 2.656 times 10 to the minus 23 grams. All very random, small numbers. But if you do the conversion, if you set up dimensional analysis using this new unit as a conversion factor, out would come the answer that an atom of hydrogen weighs 1 AMU. Carbon weighs 12 AMUs. And oxygen weighs 16 AMUs. I don't know about you, but I would much rather use these AMU numbers, 1, 12, 16, than having to use these very strange little teeny tiny exponent numbers. It makes my life much easier to just convert them to a different unit. The nice thing is that because we can use the mole, the conversion factors work out nicely using this mole value so that a mole of carbon weighs 12 grams. A mole of magnesium weighs 24.3 grams. A mole of copper weighs 63.5 grams. So 1 atom of carbon weighs 12 AMUs. 1 atom of magnesium weighs 24.3 AMUs. 1 atom of copper weighs 63.5 AMUs. Do a bunch of dimensional analysis using our mole as 6.02 times 10 to the 23rd, and out pops the fact that we can just basically swap the unit out and use these very convenient numbers. If Avogadro had picked a different number for the mole, this wouldn't work and we'd have to do dimensional analysis every single time. So we now have conversion factors that we can use to convert back and forth between a mole and a gram, and we can use them just like normal dimensional analysis. That is called the molar mass. How much does 1 mole weigh? We just have to use our periodic table to do this. So if you look on your periodic table and you find bromine, you can see that 1 mole of bromine is going to weigh 79.9 grams. If you find tin on your periodic table, you can see that 1 mole of tin is going to weigh 118.7 grams. Now for this class, it doesn't really matter if you have 1 or 2 decimals. Please don't round to a whole number. That's a little bit too much rounding. And in our class, we don't go over all the rules for rounding and how you know how many decimals to use. So just be reasonable. Use 1 or 2 decimals and that'll be more than fine. If we want to find the molar mass of a molecule or a compound, It's a little bit trickier, but we're still going to use the periodic table. What we're going to do is we're going to find each individual element on the periodic table, and we're going to add together all of the pieces to see how much the entire molecule weighs. We don't want to have some big chart where we look up the molar mass of every single molecule that exists in the world. That would be totally annoying to have to do. But if we have the periodic table with us, we can calculate the molar mass of any molecule by adding up the pieces. So calcium chloride is made up of 1 calcium atom and 2 chlorine atoms. Looking at the periodic table, I can see that calcium weighs 40.1 grams per mole and chlorine weighs 35.5 grams per mole. If I add those up, I have 1 calcium and 2 chlorines. The molar mass of calcium chloride is 111.1 grams per 1 mole. So that means if I have 6.02 times 10 to the 23rd of these molecules and I weigh them on my scale, it's going to weigh 111.1 grams. For this one, I look at the periodic table and I see that nitrogen weighs 14 grams per mole and oxygen weighs 16 grams per mole. I have 2 nitrogens and 4 oxygens. So when I add them all up, I get 92 grams per mole. I like to use parentheses and multiply them out, but if you didn't want to, you could just write 14 plus 14 plus 16 plus 16 plus 16 plus 16, and you will get the same answer. I think multiplying them in parentheses like you see on the screen is a little bit safer and it's a little bit faster. When people add up every single atom, they often miss one or they add an extra because they lose track. So I think the way you see on the screen is a little bit safer. All right, I'd like you to try this one. I'm going to pause why don't you pause the video, and when you unpause the video, the correct answer will be on the screen. All right, hopefully you paused it and you gave it a try. For this one, we have aluminum hydroxide. Whenever you see OH connected together like that, we give it a special name called hydroxide. So this is aluminum hydroxide. We have 1 aluminum, we have 3 oxygens, and we have 3 hydrogens. I know that I have 3 oxygens and 3 hydrogens because just like in math class, you're going to distribute this 3 to anything that's inside the parentheses. So this is the same as saying that I have aluminum, and then I have 3 of these hydroxide combos. So if I have 3 of these special groups, you can now see why I know that I have 3 oxygens and 3 hydrogens. So then I use my periodic table. I find out that aluminum weighs 27 grams per mole, oxygen weighs 16 grams per mole, and hydrogen weighs 1 gram per mole. I'm going to use the parentheses just to make sure everything is a little bit tidier. I took out the units here so that it would fit on my screen, but you could always put them in your work so that it is a little bit more finished. And I find out that I have 78 grams per mole is how much aluminum hydroxide weighs. All right, everybody, I hope that was helpful. Bye.